Today, we'll be covering the process of converting an existing cable design in Xpedition System Designer to a rigid flex PCB. The cable logic will simply be copied to a new board design in System Designer and relayed to a new flex PCB in EDM. The physical board geometry will be modeled in the mechanical domain, Siemens NX, and sent to the electronics domain for routing. The cable being substituted with the rigid flex solution in this demo is designed to connect the system controller board to 3D sub-connectors found on the EBSD chassis. A rigid flex solution is defined as a single PCB design, a mix of rigid boards and interconnected flex substrates of different stack-ups, all manufactured on a single panel. Rigid flex designs are becoming increasingly popular due to their unique design capabilities. Rigid flex PCBs can be used in lieu of cables to reduce weight and space requirements, but other advantages of a rigid flex design can be seen in minimizing design complexity while increasing lifespan in dynamic bending situations. In this demo, we'll create a rigid flex PCB in Xpedition System Design. We'll then replace the existing cable connectors with board connectors and sync the Xpedition System Design with the newly created flex design project in EDM. We'll then model the physical board outline and place critical components in Siemens NX, and then import the board back to Xpedition Layout and route the board. We'll then finally place the rigid flex design in the overall EBSD mechanical assembly. And with that, let's get started. First, we can observe the overall EBSD or electronic board system demo mechanical assembly. This is the mechanical view of the demo system design we'll modify in EDM. Specifically take note of the cable connecting the SC100 board to the chassis. This is the cable that is to be substituted with the new rigid flex design. The design will consist of 4 separate rigid areas bridged together by 3 flex board regions. To start building the rigid board, we'll need to create the connectivity logic in EDM. Opening the EBSD project folder in EDM, it can be seen that all the separate PCB projects, cables, and output information are stored along with the overall system design. Opposed to storing possibly out-of-date system connectivity in places like Excel, System Design allows system engineers to store live connectivity between all the boards and cables included in the electronics system, and allows them to observe downstream effects of possibly board or connector changes. This design data can be managed in System Design and forward or back annotated between boards and cables and vice versa. Throughout the system design are many different views of individual boards and cables. Designers can instantiate, for example, multiple views of the same board showing connection logic for separate boards. On sheet 4, a view of the SC100 board and BP100 board is shown with specifically the connectors linking those two boards. But on page 1, another view of the BP100 board is shown, including the connectors linking the BP100 board to 3 other boards in the system. Both of these views of the BP100 board do not need to include the entire board construction, but instead the logic specifically linking it to other pieces of the design. On sheet 5, one view of the SC100 board is shown along with its logical connection to the cable that we're going to be replacing. Using mating visualization, the designer can validate and observe pin pairing logic to eventually be used in the Flex PCB design. This visualization tool can be toggled on and off. Although we saw that the connector on the SC100 board was mounted to the board itself in the mechanical assembly, the EDM librarian also noted this was a board connector within the metadata stored in EDM. The connector above is the cable connector that will need to be replaced by a board connector. If there is a board connector that is compatible with the connector on the SC100 board, the SC100 can remain the same. In this case, the librarian has found and created a new part for the library of a compatible mate which can be mounted to the board instead of a cable. We'll unmate the cable connector so that we can place the new board connector on the rigid flex board. Now that the cable logic is disconnected from the SC100 board in the system design, the new flex board logic can be constructed. This logic can be created right next to the existing cable. The existing cable logic does not have to be deleted, but instead can be saved for use later if desired. It can remain on the schematic as it is no longer connected to the SC100 board. We will make the new flex board right next to the cable so it is easy to copy the signal logic for the connectors. It should be noted that in the next few steps, we are making a brand new board within EDM. This board will be forward annotated to a new PCB later in the process. This method would be considered the top-down approach to creating a new board, working from the system design to the smaller PCB. EDM supports both top-down and bottom-up design processes. We just as easily could have created a new board with all the needed connectors and placed that in system design and connected it to the SC100 board. Starting the top-down process, we'll need to place the new connector. The 4101-1090 connector was the cable connector we previously unmated, so we'll place the other possible connector mate, 4101-1144, as we know this must be the board connector the librarian has added. In the databook window, the desired Samtec 4101-1144 board connector is singled out. You can also see the board connector attribute is called out. Place the connector in the schematic using the Connector Pin Manager. Connector Pin Manager allows the designer to easily instantiate pin signals without having to name each individual pin on the schematic after the connector is placed. Here we will simply copy the signals on the existing cable connector. After the desired connector is in the schematic, it still needs to be logically mated to the SC100 board connector, similar to how the cable connector was previously unmated. The remaining 3 connectors will be placed using a databook search. The signals for these 3 board connectors will be copied from the signals on the existing cable connectors the same way we copied the signals for the 30 pin. Now that all the connectors are placed on the schematic, the inner board connectivity needs to be complete. For this simple board, a single bus can be created. Again, this logic will then be synchronized with a specific PCB in EDM. We will create the bus across the board and drag the signals to connect the bus to the connectors. Notice how the color changes once the signals are dragged to the bus and automatically connected. Following the top-down design approach, we will now need to create a new PCB project in EDM. Creating a new board container will allow us to link this new logic in System Designer to an individual project that can be managed in sync with the system. This container will store the board schematic, layout, bill of materials, and other fabrication info. When creating the design in EDM, Xpedition Designer will automatically be checked out and open. Check to make sure that the design is set up the way you'd like. Now that the project and schematic are created, we'll go back to Systems Design and link the newly created Flex schematic in EDM for the ability to forward and back annotate between System Design and the individual project. Once the system design is linked, we'll forward annotate this logic to the PCB. Now that the synchronization bundle is waiting, check back out the Flex schematic in EDM. Upon open, a notification bar will run across the top of the schematic, noting that there are system design forward annotations waiting to be applied. Using the Synchronization Assistant, the designer can view a list of to-dos on the left side of the pop-up screen. Designers can easily drag and drop the design into the schematic. Pieces of the design that are not yet synchronized will stay red and continue to show up as a to-do until they are placed in the schematic. Because this design is being dropped into a blank schematic, they can be area selected and dropped in one action. When forward annotating or checking in, a layer import dialog box will appear. This is because Xpedition knows the next step is to create the associated layout project, but needs to know the desired stack-up information. In this case, we'll use the Rigid Flex 4-layer template. When creating the layout, EDM will use the board template we just selected along with the design data that has now made it all the way from the system design through the individual board schematic. Before preparing the layout to send to NX, we'll need to bring in this design data we just mentioned. It is best practice for the mechanical designers to position critical components such as connectors as they are aware of more mechanical design constraints in relation to the entire system. In order for the mechanical designer to know the parts that need to be positioned, the electronics engineer will need to provide them the bill of materials. The bill of materials can be directly sent to Teamcenter from EDM, but without using Teamcenter, a bill of materials can be sent as a baseline file containing the template board and all the board components. To populate this baseline file, all parts need to be placed. It does not matter where they are placed, as the mechanical designer will be redesigning the board to the required geometry. Observe the PCB in the 3D view. This is what's going to be sent to the mechanical domain. We will now send the bare board along with the components to the mechanical designer to read into NX. The mechanical designer will redesign the board outline to fit the mechanical constraints of the system assembly and position critical components. The part we have opened in NX is simply the start of a sketch the mechanical designer will use to create the rigid board regions of this board outline. Before being able to move on, the mechanical designer needs to read in the baseline sent from the electronics domain to know the bill of materials. NX has many different applications that can be used for different modeling techniques, but in this case, the PCB exchange application provides a method of exchanging information with Xpedition. Reading in the baseline from Xpedition will bring in the bare board along with the 4 components the electronics engineer placed in the design. Before the components can be properly positioned, the board geometry needs to be modeled, so the components will be hidden temporarily. And the board itself is a template board, so that can be deleted. Now that the design area is clean but still contains the PCB's selected components, the mechanical engineer can proceed in designing the board outline. For this project, we will use the flexible printed circuit board application. In the flexible PCB application within NX, engineers can model board areas to specified thicknesses representing board stack-ups. Multiple board area thicknesses can be saved in the layer scheme editor. We will specify the thickness and offset of this design in Layer Scheme 3 to match what is shown in the Stackup editor in Xpedition. We will also rename these 2 zone names to Flex and Rigid. Now we can begin to create the Rigid Flex board design. Using the planar segment command, a sketch outline can be used to create a rigid or flexible board outline. Like we said earlier, these 2 sketches will be used to create the 4 rigid board areas of the new design. Using the planar segment command, NX allows us to create a secondary board area off the face of a base board area. Using the lower rigid board area, we'll sketch a flexible board region that will be used to bridge the 2 connector pads or rigid board regions together. This will begin to make this design look more like the cable that is being replaced. And then we can assign the flex zone thickness we have saved in the layer scheme editor earlier. Next, we'll use NX's ability to bend the flexible board area towards the top of the vertical rigid board region. Bends in flexible PCBs can be modeled in NX in different ways, but in this case, we'll bend across a sketch that we will create. We will bend all three flexible regions similar to this first sketch. Now that we have created a flexible board area and bent it up to the proper position, we can use the bridge transition command to finish the connectivity between our flex and rigid boards. Simply select the edges to be bridged along with the starting point and specified width, and NX has the ability to do the rest. This command can connect board regions with varying stack-ups. Next, we will create a second flexible board region to bridge the next connector pad to the first rigid region. The sketch for this second bridge will be much easier. All in all, we will follow the same few steps for all three of these flexible regions. First, sketch a flexible area off the base rigid board, then bend the board, and finally bridge the flex board to the other rigid board. So here, like I said, bridge the second flex area to the second rigid area with the bridge transition command. And following the steps a third time, create the last leg of the flex PCB as a mirror of the first flex region. Now that the board outline is complete, a flat solid needs to be tagged for export to Xpedition. This flat solid will be used in 2D route and place mode within Xpedition Layout. Creating this flat solid is easy when using the command provided in the NX Home toolbar. Here, we'll unhide the components that were imported from the first baseline file from Xpedition. Like we said earlier, these components will be positioned by the mechanical designer due to the fact that they have the best knowledge of how the components should align in the overall mechanical assembly. At this point, the mechanical designer can add this PCB part file to the overall assembly and check the alignment of the connectors with the chassis mounts. Now we'll move to the PCB exchange application to prepare the file to be sent. To send the design correctly to Xpedition, we'll need to set a datum coordinate system at the bottom left corner of the design. We will also refresh the PCB Design Navigator to update all assigned component and board attributes in NX. And finally, we can publish the PCB to send the data back to Xpedition. Opening the design from EDM just as we left it, we can observe the components are still sprayed outside of the template board outline. Before reading in the new file, unplace the components, delete the bend area, and generate a single route border for the base board. When MCAD Collaborator is open, you can see that the file is waiting that has just been sent from NX. Once we apply, we can see that Xpedition read in the flat solid pattern we set in NX. Using display control, we can view the PCB with the bends applied. Xpedition and NX are now in sync. But no route border was sent in the file from NX to Xpedition, so we'll generate a new route border using the generate route borders command. We now have an opportunity to route the board before placing the board in the mechanical assembly. Now that the board is fully routed, not only are the geometries in sync between NX and Xpedition, but the board is capable of replacing the cable mechanically and electronically. Through one last data exchange, NX replaced the solid bodies we created for the rigid and flex regions with PCB board appearances we have set within the PCB exchange application. I've gone ahead and added the final PCB to the overall mechanical assembly and aligned the file to where it should sit within the system. Taking one last view of the cable, we can hide it and make visible the new rigid flex design. We have now successfully replaced a cable with the rigid flex PCB.